Okay, so let's remember where we are. What we've been doing in the last couple of classes is sort of trying to understand this connection between online sequential decision-making algorithms, no-regret learning algorithms, and the minimax theorem. And in one direction, at least, we saw the connection was quite tight. If you gave me a no-regret learning algorithm that worked in some context, like the expert setting or the online convex optimization setting, then I could turn around and give you a minimax theorem that worked under the same conditions. Okay, so if you started out by knowing that you could solve expert learning problems over finite decision spaces, you could get something like von Neumann's minimax theorem, which talks about matrix-valued games with finite action spaces. If you knew about online convex optimization, you could get something like Zion's minimax theorem that just requires, convex action spaces and convex concave utility functions. Okay, and although the minimax theorem itself is sort of non-constructive, the fact that we proved it algorithmically, we saw last class, actually sort of gave us something very close to a constructive version of it. Like, not only in the thought experiment that we used to come up with the proof of the minimax theorem did we sort of think about simulating play of a game using no-regret learning algorithms. We saw that if computationally we actually have the ability to implement no-regret learning algorithms, or even sometimes slightly weaker objects like value oracles for the players, that gives us sort of an effective way to actually compute min-max and max-min equilibria in games. Okay, so that's cool, but the connection goes deeper than that. And so what I want to do today is start going through a reduction in the other direction. Okay, like not only do no-regret algorithms give us minimax theorems, but minimax theorems give us no-regret learning algorithms. Okay, and actually, like, what we've been doing in the class so far is a little bit ahistorical, right? We sort of derived no-regret learning algorithms and then used that to prove variance of the minimax theorem. Now, in the real world, the minimax theorem was proved first. It was proved by von Neumann in the 1920s, at least the the sort of linear version of it. And so, I want to go through the exercise today of saying, even though this isn't how it happened historically either, but I want to go through the exercise today of saying, okay, well, suppose I knew the minimax theorem. Suppose there I am in 1930. Von Neumann has told me the minimax theorem. Could I use that to derive from first principles multiplicative weights? All right, the answer is yes, you could have. And my hope is that this will also make some of these no-regret learning algorithms a little bit less mysterious. Right? There's some sense in which, when you teach multiplicative weights, or even worse, when we get to some of these swap regret learning algorithms, it looks like I'm pulling some object just like out of a hat and have in mind some slick analysis for it. But where did it come from? We're going to sort of go through a first principles derivation of where it might come from, driven by the minimax theorem. Okay, so questions about the premise of today's class? Okay, so you could do this for, your favorite setting: online linear optimization, online combinatorial optimization, online convex optimization. But just to sort of keep things manageable, I want to go through a case study of doing this for the simplest online prediction problem we've seen, like the expert setting, which, of course, as we've seen already, kind of implies online linear and therefore online convex optimization. But just to remind ourselves of sort of what this setting is. Okay, so in rounds, 1, the learner picks a distribution call the rounds t. So in round t, the learner picks a distribution pt. Let's say there's k distinct actions. So this is a distribution over these k actions. Okay. Then, with knowledge of this distribution, the adversary picks a cost vector. Call that CT. That's also a vector, or that is a vector of losses. There's k entries in this vector corresponding to the losses for each of the k actions that the learner might pick. Let's say that the losses are scaled to be between 0 and 1. And then the learner's expected loss if they select an action uniformly at random, or not uniformly at random, if they select an action at random according to this distribution over actions PT, well, what's their expected loss? Well, it's the loss they get if they play action 1 times the probability they play action 1, plus the loss they get if they play action 2 times the probability they play action 2, which is just, and we can write that as the expectation where the action is drawn from PT of the ith coordinate of this cost vector, which is just the inner product between PT and CP. Okay. And again, just recapping, if we're trying to derive, an algorithm like multiplicative weights or something like that, the way we're gonna measure performance is with regret. Okay, and so, maybe we're used to thinking of regret as the difference between the cost we obtain and the cost we would have counterfactually obtained with the best fixed action in hindsight. But it's going to be useful to sort of break that down into regret to each of the particular actions. I might have some regret to action 1. I might have some regret to action 2, so on and so forth. And my overall regret is my maximum regret to any of the actions. But it's going to be useful for us to do the accounting in a little bit of a finer grained way now. Okay, so remember that after T rounds of interaction, say, we sort of speak of this transcript, which we denote by pi, to sort of keep track of just the accumulated record of what has happened so far. So our regret, given a transcript of what's actually occurred, our regret to action I is just the sum over all of the rounds of the cost of the learner. Let's say that the cost of the learner is the cost of action I, IT, if the learner picks action IT at round T. Okay, so the difference between the actual realized cost of the learner and the cost of action I. Okay, so the regret is positive if cumulatively the cost of the learner is higher than the cost would have been had he just consistently played action I every single day. Yeah. there's no assumption at all in this setting about what the costs are, but besides the fact that they're vectors whose coordinates are bounded between 0 and 1. So we're not assuming that there's like a perfect expert or anything like that. We just want to do as well as the best expert in hindsight, however well or poorly that is. Yeah. Okay, so we can talk about our regret to expert I. And our overall regret, our cumulative regret, this is sort of the thing we've been bounding when we think about these algorithms like multiplicative weights or online gradient descent. Our overall regret is just the maximum over all of the actions of the regret that we have to that action. Okay, so our, we've got the regret to action I. Our regret will be maximized for the best action I, the action I that in hindsight would have led to the lowest cumulative loss. And so our regret, this thing we've been talking about, throughout the whole class, that's just the maximum over all of the actions I of the regret to action I. Okay. Okay, but like suppose we don't know about multiplicative weights, we don't know about any of these algorithms. We just, all we know is the minimax theorem, and someone has told us that our goal is to come up with an algorithm that guarantees that the regret is small. Okay, what do we do? The idea is pretty simple. There'll just be some, algebraic shenanigans involved in making it like work. But here's the idea. We're sort of going to think of the problem of designing an algorithm that has worst case regret guarantees over all possible sequences as the act of playing in a zero-sum game. What's our strategy space as the learner? Well, it's the set of all algorithms we could pick. These are just mappings from transcripts, stuff that's happened in the past, to distributions PT, distributions over actions to choose today. What's the strategy for the adversary? Well, the strategy for the adversary is basically the set of all algorithms the adversary could play to come up with cost vectors. So mapping similarly from transcripts of what's happened to cost vectors they could pick. Now, once we fix an algorithm for the learner and an algorithm for the adversary, this is just, some well-defined distribution that chugs along and generates a transcript. And so whatever transcript it generates will have some regret that we can just evaluate. Okay. Let's say that since we have a strategy space for the learner, all algorithms they could use, a strategy space for the adversary, all algorithms they could use, picking a strategy for each of them induces a distribution over transcripts for which there's some expected regret. Well, what's the objective function in the zero-sum game we want to analyze? It's expected regret. The learner would like to minimize it. The adversary would like to maximize it. Okay, now, what's really happening when we have to write down an algorithm, and promise that it does well against all possible adversaries, that's committing first to a strategy in this zero-sum game and telling it to the adversary, because saying that it does well against all possible sequences of cost vectors is like saying, even if the adversary best responds to our algorithm and picks the worst possible sequence of losses, worst possible in terms of maximizing our regret, even then our regret will be small. Okay, so in committing to an algorithm and proving a regret bound for it, we are making a claim about the minimax value of this game. We're the minimization player. We're making a claim about what happens when we go first, commit to the algorithm, then the adversary goes second and best responds so as to maximize our regret. We're saying the minimax value of the game is small. Okay? Now, this is a zero-sum game, and so if we can set things up so that we satisfy the conditions of the minimax theorem, and that's where some of the technical complications are going to come in. If we can set things up in that way, then we will know that the minimax value of the game is equal to the maxi-min value of the game, meaning we can analyze things as if the adversary moves first and the learner best responds. Now, what does it mean if the adversary goes first and we get to best respond? It means that whatever's happened in the past, fixing whatever transcript there is, when it comes time for round T, we now know, because we know their algorithm, what the distribution on CT is going to be. Like, we know what the cost vector is going to be at round T. Well, if we know what the cost vector is going to be at round T, it is incredibly easy to have low regret. We just pick the action corresponding to the lowest cost action, which we know because the adversary was kind enough to tell us ahead of time. Because in this thought experiment, the adversary is going first. So if the adversary goes first, it is going to be transparently clear that we can get low regret, right? It's easy to make predictions if you already have been told what the answers are. And the power of the minimax theorem will be to tell us that even if we commit to our algorithm first, even if we go first in this game, we can do just as well. Okay, so that's going to be the basic logic of the argument. Of course, making this work will have some details. Yeah. Yeah, good. This is an important point, right? So like, what makes it seemingly hard to think about this problem and would sort of make all of this computationally intractable, so something we want to avoid, is that the actions I pick today through the transcript affect not just my cost today, but my cost in all future rounds. And so if my goal was to minimize my cost in some absolute sense, even if I knew what the adversary's algorithm was, so information theoretically, I have enough information to like figure out what I should do to minimize my long run cost. It might be computationally intractable to figure out how to do that. But this is, a good point you've made, a key observation, that given that the goal is just to cause the regret to be non-positive, I don't need to do that. I don't need to think about how my actions today affect what cost vectors the adversary will choose in the future. Because no matter what cost vectors they choose in the future, if I myopically just choose every day the action that corresponds to lowest cost today, my regret today to all actions will be non-positive. And therefore, if I can do that every day, my cumulative regret will be non-positive. And so this is what's going to, right, so like, so far the way I've described things is just an existential argument. You apply the minimax theorem. But like, actually, we're going to want to get like an algorithm in our hands. And a reason why we're going to be able to do that is because we don't need to solve this whole zero-sum game over all of algorithm space, which would be huge. The argument's actually going to decompose round by round. Yeah, so a good point. Good. So that's sort of like the high level bird's eye view. Yeah. So like, when can you not apply like a seemingly magical argument of this sort? So first of all, like, oh, okay. So there's two parts. Two parts to this question. One is, when can I apply min-max arguments? And then maybe the other is, why is it going to be the case that like I don't need to consider min-max arguments, the intractable min-max arguments over all of algorithm space? I can limit myself to sort of local conditions. You can apply min-max arguments very, very broadly. So there's a whole general class of, you have to make sure you can set things up so that the min-max theorem applies. So it's important that, like, we're predicting distribution so that the strategy space is convex. Like, if I didn't allow that you predict distributions, the min-max theorem wouldn't hold. But quite broadly, this kind of thing holds. And so a thing you'll see across lots of online learning is that the rates at which you can solve problems in adversarial settings are usually the same as the rates at which you can solve them in distributional settings. And the reason is the min-max theorem. When you swap the role of the adversary and the learner, you put what was previously an adversarial problem into sort of a distributional framework. Oh, okay, and then when can you do it sort of locally instead of min-maxing over all of algorithm space? That has very much to do with the objective being linear. That sort of the regret is a sum over all of the rounds of like per round regret. And so if I can make sure that per round regret is non-positive for every action in every round, that's enough. So we'll see later, we can do this with calibration too. That's another linear objective. And maybe we'll, depending what I do when I run out of the notes I've written so far, like you can apply the min-max argument of the min-max arguments of this sort in extreme generality. You can sort of give algorithms or prove the existence of algorithms that can sort of pass arbitrary tests that you might have for distinguishing informed forecasters from uninformed forecasters. They can test things like regret, calibration, or anything else. But in general, implementing those kinds of algorithms is going to be computationally hard, basically because when the objective is no longer linear, then you can no longer sort of min-max round by round. Then you need to min-max over all of algorithm space. That's right. Yes. Yes, so you can almost always apply min-max arguments, assuming you're willing to convexify things by allowing randomization. The min-max arguments correspond to efficient algorithms, morally speaking, when the thing you care about, the evaluation metric, is linear, as separate a sum over time steps. Okay, good. Other questions? Yes. Oh, well, there's like all sorts of stuff. I could measure, I don't know, the variance of the payoffs that I've gotten. I could not just ask that your regret go to 0. I could sort of check what the rate at which your regret goes to 0. You can sort of think of all sorts of ways in which you could evaluate a sequence, and not all of them are linear. Good. Ira. CLT is like historically, like what was the actual, or what is the cost of the actual action they took at round T? Yeah, that's right. So like, this is like, you know, let's say that every day they sample from a distribution and actually pick some action IT, and then this is sort of like the realized regret, and then the expected regret is we will take expectations over CLT, where CLT will be a random variable. Good. Other questions? Okay, so the general idea is, you know, pretty simple and beautiful. Like we're gonna like just apply the min-max theorem. But, you know, like there's some complications, right? Like we need to like frame this in such a way that the min-max theorem actually applies. And to remember, like, what are the conditions of the min-max theorem? Well, both players need to have convex compact strategy spaces. That's actually already true here because, you know, the predictions of the cost vectors already form a convex set, and the actions of the learner are distributions, so they form a convex set too. But then the objective function has got to be convex concave. It's got to be convex in the learner's action, and the learner's minimizing, and concave in the adversary's action. And our objective, as we've described it, is this like regret thing. And there's this maximum here. And, this is like not a very well-behaved function. Yeah, it's if we just say that's the objective, then we're going to sort of run into trouble. So the first step is going to be to define a sort of proxy objective that we can use to upper bound this thing reasonably tightly, but that will have analytically nicer properties that are going to allow us to apply the min-max theorem. And so, like basically we sort of want to smoothly approximate this max. And so if you're a machine learning person, maybe the thing you immediately think is softmax, right? Like if you do like differentiable machine learning, maxes are like always annoying, and people generally approximate them by softmax functions, which are sort of sums of exponentials. Okay, so that's maybe if you come from a machine learning background, your first instinct here, and that's what we're going to do. So let's define at each round t, let's say softmax surrogate for our regret bound here with parameter eta to be, I'll write this L of pi t. Instead of a max, I'm going to write a sum. So it'll be the sum over all of the actions of the exponential of eta times the regret as measured according to this transcript to action I. Okay, so rather than a max, it's a sum of exponentials. And maybe just to sort of give some intuition for why this might be like a reasonable thing if you haven't seen like a softmax before. Okay, so in general, like sums of non-negative things upper bound maxes. And when you take an exponential of something, you're sort of exaggerating differences. If something, if my regret to action 2 is just a little bit bigger than my regret to action 1, the exponential of my regret to action 2 is going to be a lot bigger than the exponential of my regret to action 1. And so like maybe the intuition here, we'll prove a lemma in a moment about how closely this approximates the max. But the intuition here is that, okay, like a sum is going to upper bound a max. We're going to take a log outside of this, by the way, to sort of undo the exponential. But a sum is going to upper bound a max, and it won't upper bound it by that much, but it won't be sort of too loose if the largest term in the sum is much larger than all of the other terms. And so the effect of taking the exponential is to sort of mitigate this fact that we're sort of overcounting by summing up over k things instead of taking the maximum over k things. Like we're not overcounting by that much if one term in this sum really dominates. That's maybe the intuition. Okay, and you've seen this before if you have done differentiable machine learning. Okay, but the claim is that, first of all, like, why is this going to be useful? For two reasons. One is we're going to see this is going to give us a pretty tight upper bound on our regret. Like this, the log of this thing is always going to be bigger than our regret. So if we can make sure that this is small, our regret will also be small. And it's not going to be too much bigger. So we're not losing too much by moving to this kind of approximation. And this is a nice, smooth differentiable function. We'll be able to take, like first order Taylor series and stuff. We'll get like, friendly looking polynomials when we do that. That's going to be important in sort of trying to massage things to fit into like a tractable form where we can apply a min-max theorem. Okay. Okay. So, okay, so first of all, I claim that, at least if we take a log of this thing, it's going to be an upper bound on regret, but it's not going to be like a terribly loose upper bound on regret. Okay, so what's the upper bound statement? Okay, the claim is that for all transcripts, the regret on that transcript, the thing I actually care about, is always upper bounded by 1 over eta times the log of this softmax surrogate function. Okay, and so if I can keep this thing small, or if I can derive an algorithm via minimax argument that guarantees that this surrogate loss is small, that's also going to guarantee that the regret is small. Okay. So this is just a calculation. Let's sort of build this up from the inside. Let's say we've got some term that's like eta times the regret. Okay. We want to prove that 1 over eta times this is small. Well, what's the regret? The regret is just the maximum over the regrets to each of the k actions. So eta times the regret, that's nothing more than the maximum over the k actions of eta times the regret to action I. Okay. I can always, like, you know, add 1 to anything I want as long as I then subtract 1 later. Similarly, I can always exponentiate anything I want so long as I take a log later. So this is, you know, equal to the log of the exponential of the maximum over all of the experts of eta times the regret to that expert. Right, like I'm not doing anything smart here. I've just taken an exponential and I've immediately like undone it by taking a log. And, you know, an exponential is like a monotone function, right? So the exponential of the max of a bunch of quantities, that's the same thing as the max of the exponential of each of those quantities, because exponentials are monotone, and so it preserves the relative ordering of quantities. So this is equal to the log of the max over all of the actions of the exponential of eta times the regret to that action. Okay, I've just interchanged the max and the exponential, which is okay because the exponential is a monotone function, so it's making everything bigger, but it's not changing the ordering of any two things. Okay, now exponentials, these are like non-negative functions, right? Like, you know, no matter what the regret is, the regret could be positive or negative, but the exponential of the regret is greater than or equal to 0. Which means that the maximum of these quantities over all of the actions can only be smaller than the sum of the quantities. But if I have a, if I sum up over a bunch of non-negative terms, that's only larger than any one of them. In particular, is only larger than the maximum. So here's actually the only place where there's going to be like an inequality here, not just an equality. This is at most the log of the sum over all of the actions of the exponential of the regret to that action, which is just the log of the softmax surrogate loss. We've sort of derived the softmax surrogate loss. Okay, so just divide by eta on both sides, and that's the statement of the lemma. Okay, so that's maybe how you would like come up with the softmax surrogate loss if you didn't know about it already. Okay, so it's an upper bound on the regret. And really what's happening is just, it's this log sum of exponentials, which is upper bounding a max in sort of a nice continuous differentiable way. That's a very general thing, not specific to regret. Log sum of exponentials, upper bounds max. Okay. Maybe just as a sanity check, like, fine, like we get like an upper bound on regret, but like you might be worried that like we've already given up the game, that this thing is just such a loose upper bound on regret that even if we can make this small, like we can't possibly hope to get the regret itself to be small or something. And I just want to note that this is actually a pretty tight upper bound on regret. So how do we know that? Well, what is this loss? It is the sum of the exponential of the regret to each of the actions I. What we care about is the regret to the, best action I. So we care about like one of these terms. Right? Like we care about the largest of these terms, the largest regret term. And so in the worst case, all k of the actions have the same regret. All k of the actions are tied for like best action. Okay, so in the worst case, this quantity is at most k times e to the eta times regret. Right, like this would be realized if all k of the actions had the same regret. Okay, so the max was just equal to the value of any one of them. Then we would sort of, in this sum, be overcounting by a factor of k. Okay, so this is the worst case. But in this worst case, like what is log of the surrogate over eta, this quantity that we're really using to upper bound regret? Well, it's at most the true regret, right? The log cancels out the exponential and the 1 over eta cancels out the eta. It's at most the true regret plus log k over eta. Okay, so this is a quantity that's always upper bounding our regret. And it's not too loose. The sort of degree to which it might overshoot regret is bounded by a logarithmic term in the number of actions. Okay, so again, nothing to do with regret. This is like a general property of the softmax function. Softmax upper bounds max and doesn't overshoot by more than log the number of things you're taking the max over. Okay, so questions about this? This little bit has nothing to do with regret or min-max arguments or anything really. It's like probably just a general fact to keep in mind. It's often the case that maxes are annoying functions to work with. They're not continuous or differentiable. This is a very nicely behaved function, and it's a very good proxy for a max.
The regret to every single action is the same. Like, what would be the best action then? Like, shouldn't there be one that's
Any one of them. Could be that they're all equal. You know, like the payoff for every action is like a coin flip. It doesn't really matter what you do. Okay. So, you know, we wanted to control this thing. I claimed this thing was annoying to work with. But now we've got the surrogate loss, which I claim is like less annoying to work with. And what we know is that the surrogate loss gives us a good upper bound for the thing we want to control. And so our strategy from this point forward is going to try to derive an algorithm via the minimax theorem that promises that the surrogate loss never grows too large. Okay. Okay, now we had a little bit of this discussion already. The way I initially described how the argument might work is as a min-max argument over all of algorithm space. My action space as the learner is the set of all algorithms I might use. We could do that, but then like when it comes time to actually trying to write down the algorithm for the learner, we'd have this like giant intractable min-max problem to solve, right? Algorithm space is really big. And so I don't want to do that. I want to implement sort of what we discussed a little bit as the greedy strategy. I'm sort of gonna ignore the effect that my action will have on the future and just try to, you know, the future beyond like the next round, and just try to play so that my one round increase in this surrogate loss is as small as possible. Okay, if I can guarantee that my, you know, at every round the expected increase in my surrogate loss is small, then just by iterating this argument over each of the rounds, my overall surrogate loss will be small in expectation. If it never increases by much, it can't grow very large. Okay, so my goal, and here this is going to, like the reason we're doing this instead of min-maxing over all of algorithm space, which would also work. The reason we're doing this is because we want to set up a relatively small min-max problem so that once we're done with this existential argument, we can actually like get our hands on a real algorithm. Our goal is to sort of try to frame a min-max problem over just the action space in a single round. What should I predict at the next round? With the goal of promising that the one round increase in the surrogate loss will be small. Okay. So towards that end, I want to think about what the increase in surrogate loss looks like as a function of the action that I take and the cost vector chosen by the adversary. Okay, so some notation. Pick some transcript. Let's say pi s minus 1, everything that's happened up through and including round s minus 1. Given an action for the learner, an action I, one of their k choices, and a cost vector, C for the adversary, let's say that transcript pi twiddle s is the transcript that I would get by appending IC to my existing transcript. So it's like a hypothetical continuation where I'm imagining that at round S, I, the learner, I'm gonna pick action I, and the adversary is gonna pick cost vector C. Okay, I'm not necessarily gonna do this. I can talk about hypothetical continuations for all sorts of different actions and cost vectors, and I'm not obligated to commit to any of them, but like for any action and cost vector that might be chosen, there's some hypothetical continuation of the transcript. Okay. Okay. So now let me define delta pi s minus 1 of C and I to just be the difference between my surrogate loss value under the continuation of the transcript defined by C and I and my surrogate loss value prior to the continuation. Okay, so this is sort of like the change, were I to play I and the adversary were to play C, how much would the surrogate loss increase? Okay. Ultimately, the kind of thing we want to do is we want to come up with a distribution PT on actions that's going to promise that for all C, for all cost vectors of the adversary, this quantity, the increase in surrogate loss, is guaranteed to be small. If we can do that, we're done, because if we can promise the increase in surrogate loss is small at every round, then the surrogate loss in the end will have to be small, and therefore the regret will have to be small. Okay, so I want, like, our long-term goal is to find a mixed strategy for the learner, a distribution over the I's, that's going to guarantee that for all strategies of the adversary, this quantity is small. Does that make sense? Okay. So towards that end, I would like to get a handle on this quantity. I'd like to get a good upper bound on this quantity, and I want the upper bound on this quantity to be something that I can use as a payoff function in a zero-sum game to which I can apply the min-max theorem. Okay, so my goal is to get like an upper bound on this quantity that is linear, ideally, in the strategies of both players, so that everything will be sort of set to apply a min-max theorem. Okay, so the claim is that for any choice of eta less than 1, I can upper bound the increase in surrogate loss if the adversary plays C and I play I as the sum over all k of the actions of the exponential of eta times the regret that I already had at day s minus 1 to action j times eta times ci minus cj. That's one term. Plus eta squared times the loss, the surrogate loss that I already had at round s minus 1. Okay, so this is some like long expression. Like the derivation is going to be purely algebraic, but let's like maybe reflect first on if we can derive this, why this will be useful to us. Okay, so first of all, like here we are at round round s minus 1 has already completed. Basically, we have a transcript that it goes up to and including s minus 1. Everything before round s has been done already. It's been committed to, and sort of the things that are variables here are our potential action at round s and the cost vector at round s. We don't know what those things are going to be. Okay, but like in particular, some of the things in this expression are constants because they only depend on what's happened in the past. So first of all, this thing's definitely a constant. That's just the loss at round s minus 1. In fact, we have no control over what that is. So if we're trying to minimize this thing, we can just totally ignore this term. It's like, it doesn't depend on the actions of either players. It's something that's just been fixed. And then this thing is a constant. Each of these exponential terms within the sum is a constant because again, these depend only on the transcript that's been realized so far, everything that's happened in round s minus 1 or previous. So that's not something we can affect. The only term that actually depends on the arguments to this function, the actions for the learner and the adversary, the only term that depends on the actions to the learner and the adversary is this term. Okay? Like the index I is decided by the learner's action, and the value of the cost in each index that's decided by the adversary's action. So it's just that. Okay? And this, if we allow the learner to randomize and pick a distribution over actions, this is going to be linear in the actions of both the learner and the adversary. It's transparently linear in the actions of the adversary. It's just the difference between two of the coordinates that he chose. It's linear in the adversary's action. In principle, if we didn't allow the learner to randomize, it would be some complicated non-convex, non-continuous function of the learner's action because the learner is sort of like choosing a term I to focus on, and these quantities can be complicated. But if what the learner is doing is choosing a distribution over I, then in terms of this distribution, just by linearity of expectation, this whole thing is linear in the learner's action. Okay, and so looking at this thing, it's some long expression, but like, why is it going to, why is this upper bound going to be useful for us? It's because once we like realize that all of the complicated things that show up here are constants by the time we get to round s, this is an extremely simple loss function that we can use to define a zero-sum game that is linear in the actions of both the players, and therefore exactly the kind of thing that we can apply a min-max theorem to. Okay, so that's why this expression, long as it is going to be useful to us. Does that make sense? Okay. Yes. You mean like you're talking about how we're going to derive this? Yeah, like yeah. I mean, we're going to like do this in a moment, but like yes, like it's useful that we have like an exponent here because what's the difference between round s and round s minus 1? Well, basically, in all of these regret terms, we will add one additional term, the term corresponding to round s. And so in the exponent, we'll have the sum of two things, but e to the a plus b is e to the a times e to the b. So exponents play well with sums, sort of. Yeah, like one of the nice analytical properties of our surrogate loss that wouldn't have been true had we stuck with max. Yeah. I mean, like the game we're actually going to define, the strategy space for the learner will be the set of distributions over actions. And the thing that they're going to care about as a function of their distribution is the expected increase in surrogate loss in expectation over their choice of I. Okay, so in terms of the learner, like for every I, this is just some number. Okay, but as a function of the distribution over I, this is a linear function of that distribution, but because expectations are linear. Which is a constant. That's right. So basically, once you fix the adversary's strategy, as far as the learner is concerned, for each action I, there's just some numeric cost defined by this weird number and, the values C chosen by the adversary. Okay? But what their action set is the set of it's this probability simplex over K actions. And so what's their expected loss? It's like the inner product of this vector of numbers with the weights they place on each of the actions. Right, so like here, everything's already, you didn't need to allow randomization for things to be linear in the adversary strategy. Here, we're sort of playing the usual sort of mixed strategy trick used in game theory to like convexify things. Like we've got a learner who, if we didn't allow them to randomize, has K discrete actions that just, each of their actions has some numeric valued payoff. The numbers are weird. They don't have much structure. But now we say, okay, just find distributions over these K values. Your expected value is a linear function of the weights of your distribution. Yeah, so and this is going to be why it's important to let the learner randomize, which we already know from sort of studying no regret from first principles. Yeah. You'd get gradient descent if you used squared loss, summa. So this is another, you can get different algorithms by using different surrogates. Yeah. That's right. So in some sense, I mean, the softmax is a very natural thing to choose. Like it's, the fact that it's got like exponentials is not, it's not quite that we're just like baking in multiplicative weights here, even though, the multiplicative weights also have exponentials. Like softmax is a very natural thing to choose if you're upper bounding a max, but it's not the only thing you could choose. You could choose the sum of squared regrets, and then you'd get a gradient descent like bound. So different surrogate loss functions will, in this way, allow you to derive different kinds of regret bounds. Good. Other questions? Okay, so that's why this thing will be useful. Let's go ahead and derive this thing. All right, so we're trying to bound this increase in surrogate loss, which is just well, expanding the definition, the difference between the loss at this sort of hypothetical continuation of the transcript and the loss of the original transcript. And, you know, like what are these surrogate losses? Well, I just erased them, but we remember they're just the sum over all of the actions of e to the eta times the regret at the continuation of the transcript to action j. Okay, that's the surrogate loss of the continuation of the transcript. And what are we subtracting off? Well, it's the surrogate loss of the original transcript. It's the same sum over the k actions. So what I'm subtracting off term by term is just the exponential of eta times the regret according to the previous transcript to action j. Okay. Now, the regret to action j at this continuation of the transcript, how does that relate to the regret of action j at the previous transcript? Well, the regret to action j is just the sum over a bunch of terms, one for each time step, of the difference between the loss of the algorithm and the loss of action j. And these two transcripts agree on their prefix up to round s-1. So the only difference between these two is the additional term in the sum that shows up at round s. Okay. So this is just, you know, we can sort of expand out. We can write the regret at the continuation in terms of the regret of the original transcript. And what we get is just the sum over the k actions of e to the eta times the regret at the original transcript to action j, plus the new term in this sum introduced at round s, which is just eta times, well, the learner played action I, and the cost vector was c. So it's just eta times ci minus cj. That's the additional term corresponding to regret to action j. Okay, all of that's inside an exponential. And we're still subtracting off the same thing we were before. Okay, we're still subtracting off e to the eta times the regret to action j. Okay. Now, okay, now we're starting to get sort of some like terms here. We've got the regret to action j at time s-1, both here and here. Now here, we've got an exponential that's got the sum of two terms in it, right? It's like e to the a plus b, which is e to the a times e to the b. Okay, so let's just sort of break things out like that. So we've got the sum over the k actions of e to the eta times the regret to action j. Okay. And I want this to be a common factor in both of these terms that we were previously subtracting. Okay, so to get the rest of the first term, I've left something out. I've left this part out. To get the rest of that, well, I need to multiply by e to the eta times CI minus CJ. Okay, like e to the A times e to the B is e to the A plus B. So that recovers the first term. And the second term is actually exactly this thing. So I can just write -1 here, right? And now this is just a factorization of these two terms I have above. Okay, now what's a nice fact about exponentials? Like what's another place where we can use the fact that we have this nice well-behaved surrogate loss instead of these annoying maxes? Well, a nice fact about exponentials is that if I've got some number less than 1, then e to the x is at most 1 plus x squared. There's like a first order Taylor expansion. Now, these things aren't less than 1. Like these are big, unwieldy regret terms. But this thing is, right? This is just a single term's loss. Ci and Cj are bounded between 0 and 1. So the difference is between 0 and 1. Eta is less than 1. So this whole thing is, the thing inside this exponential is less than 1. So I can use this sort of polynomial approximation for it. Okay. So this is at most the sum over the k actions of e to the eta times the regret at round s minus 1 to that action. Okay, times, I'm going to replace this with 1 plus eta times ci minus cj plus eta squared times ci minus cj squared. The 1 cancels out with the -1 we've already got here. And so what I'm left with is eta times ci minus cj plus, well, eta squared times ci minus cj squared. But ci minus cj is a number between -1 and 1. And so I can upper bound that whole thing by just eta squared. Right. And now I'm almost done. What do I have? Well, I've got the first term here. The sum over all of the actions of the exponential of the regret that I have to that action. Okay. Plus this constant, eta squared, times the sum over the, the exponential of the regret that I have to the action times eta times ci minus cj. That part's important. Okay. This is like the first term. And then what else do I have? I've got this constant eta squared summed up over all of the actions of the exponential of the regret to that action. But that's just, by definition, our softmax surrogate loss, right? So this is just eta squared times the surrogate loss at round s minus 1. Okay, which was exactly the claimed quantity. So what we've succeeded in doing is, we've just there's this thing we really care about for the purposes of getting low regret. We want to make sure that our surrogate loss does not increase by very much from round to round. And so we've written down a quantity that is exactly the increase in our surrogate loss. And what we've just done is we've upper bounded that quantity by a function that is going to be linear in both the actions of the learner and the actions of the adversary at a single round. So we're setting ourselves up to define a zero-sum game, a minimax game defined at a single round, so a small minimax game. You could. Yeah, I mean, if you want, you can at this point. It's not clear yet what's the right value of eta to pick. You could pick any eta you want. This bound holds for any eta less than 1. Yeah, but remember, when we derived how much the softmax surrogate is overshooting the regret, okay, first of all, it's overshooting it more if eta is small. So that's a reason not to make it tiny. So why not make it 1? Well, the amount that, this says we're increasing the regret by from round to round. There's this additive term that's like eta squared times our existing softmax surrogate loss. So if eta was 1, the surrogate loss might double at every round. It might increase additively again by its value already. And so to control the growth of the softmax surrogate loss using this expression, we want eta to be small. But we don't want it to be 0. We don't want it to be too small, because the smaller eta is, the less tightly the softmax surrogate upper bounds the max. And so that's a trade-off we're going to have to manage. Yeah. Which form of? Oh, sorry. It's the first term is not the softmax loss, because the softmax loss is this unweighted sum. But here, each term in the sum is weighted by something. Yeah. So we have like the sum over a bunch of terms. Each term we have like the constant that corresponds to the constant in the softmax surrogate loss for that term. Then we're multiplying, on the one hand, that term by some number that is different term by term. On the other hand, we're multiplying it by a constant. So when we're multiplying it by a constant, it's just the constant times the softmax surrogate. When we're multiplying it by this thing, which is different for every j, it is not the softmax surrogate multiplied by something. Oh, yeah, you're saying like, could I just like upper bound this thing by 1 or something? I could. Then it would no longer be a useful bound. So like, this is the part, like basically the minimax argument is going to make the first term vanish, just to sort of look ahead a little bit, right? Because if I have to choose the action, if I have to choose my action I, after knowing, only after knowing what the cost is, then I'm going to pick I to be the coordinate of the cost vector that is smallest, which is going to make all of these terms non-positive, which is going to cause this whole entire first term to vanish. This is going to be where the power of the minimax argument comes in. I mean, it just doesn't though. Like, okay. Yeah, you're right. That's right. Yeah. So in the end, by upper bounding that by 1, I'm going to get like a root t regret bound. It is possible that, okay, I haven't done this particular derivation in that case. There are no regret algorithms that have not just a root t regret bound, but regret bounds that depend on things like the square of the cumulative square of the losses, things like that. It does seem likely to me that you could get regret bounds like that in a minimax argument like this by being more careful in this upper bound, with the caveat that I haven't actually tried to do that. So yes. You're right. I'm being a little sloppy here by just upper bounding this thing by eta squared instead of eta squared times CA minus CJ squared. I'm certainly doing it to, well, this term would be, the linear term would stay. So I guess what then you'd have a more complicated analysis, and I didn't want to do it. But it's possible you could make it work and get a more refined bound. You're never going to beat root t in the worst case, but for nice sequences, you can. Okay. That doesn't sound like a pedantic point. That sounds very important. Which inequality? Oh yeah, maybe it's going to be like, yeah, let's say that or something. Good point. Eventually, it's for small enough x, it's true.
Yeah.
Good point. Okay, other questions? We haven't yet written the zero-sum game, but what I want to, the kind of thing we want to prove is that there is a distribution over actions I that guarantees that for all C, this thing is small. So there will be no, we want to prove a uniform statement for all C, so there will be no randomness over C. So for the expectation that we are going to write down, it is going to be an expectation only over the learner's randomness at round S. That's right. That's right. The adversary never, in fact, the adversary never needs to randomize. Mm-hmm. Good questions. Other questions? Oh yeah, ha. It is true. You know, E, you know, is it? Who knows what E is? It's a small constant. It's, you know, is it bigger than 3? Is it less than 3? We don't worry in computer science. But yeah, I do think it is less than 3. Small pedantic point. Good. Okay, good. Other questions? Okay. Okay, so like, you know, where do we sit in this argument? I think the difficulty is that the recording being produced, since I'm wearing a microphone, it hears everything I'm saying, but it's not hearing what you guys are saying. So it will not be appreciated that this remark I just made about a small pedantic point was me riffing off of Eshwar's comment as opposed to like being cruel to a to a student. But okay. So obvious thing, right? Once we commit to an algorithm for the learner and an algorithm to the adversary, that induces some distribution over transcripts. We have some expected surrogate loss at the end of the day. What is that expected surrogate loss? Okay, so the expected surrogate loss is sort of like, by definition, just by writing out a telescoping sum, looking at the definition of like the increase in surrogate loss. It is just the sum over all of the rounds of the expectation over I, and the action I, drawn from the strategy determined by the learner at round t of the increase in surrogate loss from round t minus 1 to round t, conditioned on what's happened so far. Okay, so just, like linearity of expectation. So our goal now is to argue that there is a, no matter what the transcript has been realized as so far, no matter what's happened in the past, there is always, as a function of that transcript, a distribution, PT, for the learner to play at round t that will guarantee that this expectation is small. If we can do that, we will know that the expected surrogate loss overall is small, just by controlling each term in the sum here. Okay, so that's the strategy. Towards that end, let's define a zero-sum game. Okay. So let's say the round t surrogate game is defined as, well, what do we need to specify to give a zero-sum game? We need to specify a strategy space for the learner, for the adversary, and a utility function. And we need to verify the relevant conditions for the minimax theorem to apply. Okay. So the learner's strategy space, the learner will be the minimization player. So their action space, A min, will be the set of probability distributions over their k actions. This is a convex action space. It's just the probability simplex. The adversary, who will be the maximization player, has action space A max, just the set of all feasible cost vectors. We don't even need to allow them to randomize. This is already a convex set. Okay, so the adversary actually never needs to randomize. And then what's the utility function? Well, for all cost vectors the adversary might choose, for all distributions over actions that the learner might choose, the utility function in this game, which the learner wants to minimize and the adversary wants to maximize, given a cost vector C and a distribution P, we'll define that to be the expectation over an action drawn from P of the sum over all of the actions of E to the eta times the regret at round S minus 1 to action J times eta times CI minus CJ. Okay, so just the first term in this upper bound that we gave on the 1 round increase in the surrogate loss. Okay. We could have added the second term as well, but it wouldn't have mattered. It wouldn't have changed the game because this second term is independent of the actions of either player. So a min-max strategy in the one game is equal to a min-max strategy in the other. Adding a constant, action-independent constant, doesn't strategically change the game. Okay. Okay, so since we have a few minutes left, I'll continue the sort of formal derivation next class. But I think at this point, you can already sort of see what's going to happen. And so maybe let me just spend the last minute talking you through it in anticipation of actually doing it next time. Okay, so first of all, learner has a convex action space. Adversary has a convex action space. This utility function, remember these things are constants. So this utility function is linear in the actions of both the learner and the adversary. Linear, explicitly linear in the adversary's action, linear in the learner's action because we allow them to randomize and take expectations. And therefore convex concave. So this game satisfies the requirements of the minimax theorem. In fact, we don't even need any complicated convex concave minimax theorem that we derived from online convex optimization. This satisfies the requirements of von Neumann's minimax theorem. Which means the min-max value of the game is equal to the max-min value of the game. Okay? The min-max value of the game is the thing we're interested in. How well can the learner do? Is there a distribution P for the learner that guarantees that for all cost vectors of the adversary, the expected increase in surrogate loss is small? If the min-max value of the game is small, that means that if the learner plays a min-max strategy in this game, the increase per round of the regret will be small, and therefore the overall regret will be small. But that's hard to think about. So let's think about the max-min value of the game instead, which the min-max theorem tells us is the same thing. Well, what's the max-min value? Well, in the max-min order of play, first, the adversary tells us the cost vector C, and then we best respond. Well, if the adversary tells us the cost vector C, what action should we play? We should play deterministically the action that has minimal cost. Right? Then I, in this term, will always correspond to the min cost action. So Ci will always be less than or equal to Cj, which means, well, if the adversary goes first, we can always force this linear term here to be non-positive. This thing is an exponential, so it's positive. The product of a positive thing with a non-positive thing is non-positive. And so if the adversary goes first, it is like immediate from, we don't even have to think about algorithm design. Like the adversary tells us what the costs are, we pick the min cost action. It is immediate that the value of this game is 0. Okay, the max-min value of the game is 0. That's the same as the min-max value because of the minimax theorem, which means there is a distribution. There is an algorithm that the algorithm can play as a function of the transcript so far for choosing an action which guarantees that the expected increase in surrogate loss is small, which guarantees that the cumulative surrogate loss will be small. Okay, so this is exactly where the min-max magic is going to happen. We'll make this precise next time. As I just described it, it's only an existential argument. It says, well, it's easy to figure out how to play if the adversary goes first. Therefore, there must exist some way for us to play if we have to go first. But in fact, because we arranged things so that we are not playing a min-max game over all of algorithm space, we're just playing a small min-max game where the learner has k actions. It's actually going to be pretty easy for us to get our hands on what this equilibrium strategy looks like. So we'll actually have a concrete algorithm at the end of this. Okay, so we'll do that next time.